Good morning, everyone, and welcome to this webinar on a practical workflow to convert analytical fracture half-lengths to an actual non-uniform SRV with Vivek from Oxy. I'm obviously not Vivek, but I'll introduce him here in a second. Before that, I'm going to go through some webinar logistics. The first thing to just emphasize is that we're more than 150 registered participants. So everybody is muted by default, but that does not mean that you can't ask any questions throughout the webinar. So if you have any questions, use the Q&A chat box down to the right, okay, down here. The webinar will take around 45 to 60 minutes, and that includes the presentation. That will probably take 40 to 45 minutes, and then we have a Q&A session after that. And note that we are recording the webinar today, and the webinar will be distributed to all the participants and on our LinkedIn and YouTube after the webinar. The webinar is facilitated by Whitson, and Whitson exhibits its love to these kind of topics through our web-based RTA platform called Whitson Plus, where you can do everything from decline, curve analysis, PVT, bottom hole pressures, RTA, full physics reservoir simulation, and nodal. If you want to learn more about that, you can participate in some of our courses that we run every single year that you can find more information about on whitson.com/training, or if you're just passionate about these topics, you can join any of the future webinars as well. And we try to have one webinar every month. I know what you're thinking. You think that this webinar is a free webinar, and that's almost true. The only cost is that, or at least we hope that you can go and follow our LinkedIn. So if you're on LinkedIn, go to linkedin.com/Whitson and follow us to get more webinars like this, other technical content as well. The reason why we call it a gentleman's agreement is, of course, we're not there on the other side to ensure that you're actually following these rules, but we would really appreciate that. If you're going to URTEC next month up in Denver, feel free to join our rooftop happy hour. It's the day before URTEC starts. URTEC is a little bit special this year. It starts on Tuesday and not on Monday, and we've always done the happy hour the day before. So for those that come into town the day before, don't have a place to meet friends and wine and dine, feel free to join us here. It's just 8 minutes away from the conference center at the rooftop, where you can see basically the entire Denver downtown. Also, if you're really passionate about these type of topics that we're going to talk about today, well performance, completion design, PVT, bottom hole pressures, flow material balance, numerical modeling, and nodal, we have our yearly conference here in Houston, 12th of October. If you would like to participate there and would like to know more about that, feel free to shoot me an email at carlson@whitson.com for more information. So with that, we're ready to introduce the speaker. Vivek is a friend of mine that's been with Oxy for more than 18 plus years. His current role there is to be a well analysis and design manager. His master's degree is from Texas A&M here in Texas, where it's right now pretty crazy weather, I'm not going to lie. It's been for a couple of days now, too. He's written numerous technical papers, and the cool thing about what we're going to look at today, it's kind of like a mix of two of my favorite papers from last year that Vivek wrote, one for with some colleagues at Oxy, one from URTEC, and one for ATCE. So with that, my friend, I'll just unmute here and turn off my camera and give the stage to you.
Thank you, Matthias. Let me share my screen. You see it?
Perfect.
Right. All right. So I hope a lot of people here are using RTA. So if you are using RTA, you would be knowing that RTA is a very valuable tool to understand the well performance, the long-term forecast. But when we use the RTA half-length to account for your field development plan spacing, so what you would see is the infill walls come up with a lot more degraded production compared to the expected values. So the main problem here is there is some disconnect with the half-length that you get from the RTA analytical models with the field development plan. So in this presentation, we are going to give you a practical solution to still use RTA half-length to properly account for the development spacing, because it is a good tool to understand early performance. So if you can use the RTXF with confidence, I think that will be a major win for us as a technical front. So I want to acknowledge my co-author Surabe Ismaili, who has done a lot of technical contribution to this presentation. Okay, the outline here is pretty simple. We'll start with motivation and objective, and we will provide a solution to convert this RTA half-length to account for depletion. And finally, we'll wrap up with summary and conclusions. Okay, as I mentioned, there is a problem with the RTA SRV area. So you can see that here I'm going to show you an example of a 9 walls per section DSU. So we have a standalone wall producing for 3 years, and after that we drilled 8 new walls. So if you look at the geology, they are very similar within the same DSU, same reservoir fluid. The completion size is even better than the standalone. And we have captured several diagnostic tools here to understand the fracture height for different completion size. So once we have that, we did the RTA, and we have a good petrophysical model to get all our averages. So you can see that the one that I drew here, the rectangle box, that's basically the fracture length that we got out of the RTA SRV. So you can fit as many as 50 wells, with this type of smaller RTA half-lengths. But in reality, you can see that the projection is telling you the opposite story. The standalone well is still the best well. Your infill averages are lower than the standalone, and your child wells are at the bottom. So it shows you that there's interference. The well spacing matters, and your child wells are seeing the depletion. But with this scenario of RTA, I mean, you won't be capturing any of those. So why is the RTA not showing you the right half-length that you should be planning your field development based on that? So we'll find a solution for that one. But before getting to the solution, first we need to understand some of the discrepancies. What are the major causes for this low half-length that you get out of this technical analysis? So what we identified is there are 4 major discrepancies. The rest is all minor. The first one is, in a conventional sense, you would be associating the oil in place with the -1 slope. Usually this is a boundary dominated flow. So that is your indication of your oil in place. But for these unconventional systems, that is going to be a little bit of a far stretch. It may take many years, or sometimes you may not reach the -1 slope. So the industry practice is to pick the oil in place at the end of linear flow. I mean, that practice is still consistent to understand the performance early time. You don't want to wait for 3+ years to understand what is your oil in place. So you have to have some early time indication. So the end of linear flow is a very good proxy for comparing to well performance, but that may introduce some conservative estimate for your oil in place calculation. So we won't be addressing that first point in this presentation, because when we do the final conversion, empirical conversion, that one will automatically be getting adjusted with all the bulk conversion. The other 3 topics is what we would be talking about mostly in this presentation. The next one is the flowing metal balance volume is calculated based on the single phase. So it's mainly the oil phase and not accounting for the multi-phase effect. So I'll show you in the subsequent slides why it matters, why that multi-phase effect is a bigger component that you shouldn't be neglecting. And the third thing is the rectangular geometry assumptions. And most of the time we simplify the fracture geometry for easy calculation. So when you convert to a rectangular geometry, it's going to be much easier for solving the equation. So that is why we do that. But that also introduces a lot of inconsistency in what is going on in the reality. And the last one is inconsistency in the fracture height input. So I've seen like so many theories floating around. Is what is the fracture height input that we should be putting in the RTA? Um, a lot of hypotheses that okay, some think that it's a stratigraphic thickness, some put it as a fixed height, uh, you know, some pick as a lithology break or stress differences. But if I want you to understand that is since we are treating this as a rectangular geometry, any inconsistency in the height assumption is going to affect your XF calculation. It's a very simple. It's solving for the volume. So if one of the dimension is wrong, so the other dimension will not be like inaccurate. And also the averaging the petrophysical properties, because we are inputting just one number in the RTA for the entire fracture height. So should you be taking a linear average of all these properties, or should you be coming up with a different kind of weighted average? We'll be talking about those as well, because that's still a critical piece that we got to be properly accounting for when we do the metal balance. Okay, let's begin with some of the important ones that we have to fix it before we get to a meaningful half length that you should be getting out of the RTA. So we published a paper last year to account for water production. So the metal balance equation here is we are providing you a classic metal balance equation where all the major like plots that we see are all stemming from this main classic metal balance equation. So in the earlier and conventional development, we weren't seeing that much of water. So when you neglect and also these, you have a lot of high pressure in this formation, so you don't see typically gas cap. So it's all solution gas all ratio. So if you neglect the gas and water production, you get to a very simplified single phase oil metal balance. So, and if you combine with the Darcy equation and pseudo steady state, you get to a form which is plottable. You plot the productivity index, which is the normalized cumulative production, and you extrapolate that trend to get your SRV all in place. So that's a typical industry standard that what we use is a single phase. But there are, in the modern softwares, we have the capability of doing the multi-phase equations as well. But this is more like a general workflow that many people will be using. So the problem with this one is, as long as you don't produce water, it's fine. But in Permian Basin reservoirs, we are seeing a lot more formation water. So you have like water ratio, which is pretty high for the entire life of the well. So when you have that multi-phase flow comes in, you cannot neglect the water production. So you have to go back to the metal balance equation, and if you properly account for the formation water, it's part of the metal balance equation. So you cannot calculate all in place by neglecting the water production. So you can see that this term WP times BW, so that is an addition to what the single phase should be. So when you do that and do the same formulation, you can still get to a form which is very similar to the single phase. But notice that there is a multi-phase correction here. There is 1 plus WR by B sub 4R. So you have to use that. I mean, as long as if you are using single phase, if you are correcting it by using this multiplier, you're going to be close enough to have a reasonable SRV all in place. The way we tested that one using the using the simulation is we took about 32 synthetic cases with wide ranges of properties which are very common to Permian Basin. We have changes in the saturation, we have changes in the initial pressures and in porosity and so, I mean all those different properties that gives a kind of general sense of the Permian Basin reservoirs. So we did the 32 sets of synthetic cases, and for each of those synthetic cases, we have a known input all in place. So we force that input, and you got the production out of that one. So what we did was we used that output, which is the rates and the pressures, to input that in the flowing metal balance workflow to calculate what is the resultant SRV all in place look like. So if you have a known input all in place, the expectation is when you do the flowing metal balance equation from the output, it should be matching your input SRV all in place. But what we observed was when we did that conversion, so the x-axis is the model input SRV all in place, but the y-axis is what we got out of these FMB single phase equation. You can see that for every case, all the 32 cases, it is falling below that one-on-one line. So which means that you are under predicting your SRV all in place quite a lot based on the single phase formulation. So then we corrected that one using this multi-phase correction, which is 1 plus WR by B sub OI. So when we did that, you can see that now it is very close enough to get you the input that we use for using these synthetic cases. So that is how this water protection is going to be making a big difference in your oil in place calculation. So you cannot neglect that. You have to take into account the formation water that you're getting out of it. Again, so some of the recent upgrades in the softwares will always have this multi-phase correction to some extent. But if you're not familiar with the multi-phase workflow, even if you're doing a single phase, as long as you did some multi-phase correction, you should be fine with your SRV all in place. Okay, now let's go back to that example that I showed, like the pre-water correction, how small the XFs are. So when you do this correction of post-water, now you can see that your SRV size as like, it's about 3 times higher. That's because the water oil ratio in this DSU is about 3. So if your water oil ratio is higher, you're going to be seeing that the multiplier is going to be different because your B sub OI is also going to be affecting that to some extent. But yeah, you should be having different multiplier for different water oil ratio. Notice that it still doesn't explain the interference that you're seeing in the production. So the main reason is you're still using rectangular geometry even after correcting for physics, but it's not correcting for the right contacted shape. So let's address the next problem, which is the rectangular geometry assumption. A couple of years ago, we published a paper by using a pressure monitoring well in the Permian Basin to come up with the height understanding, the fracture height understanding, and also how the fracture shape is different based on modeling all of those monitoring well pressures. So we drilled a brand new monitoring well after 3 years of horizontal well production. We put that monitoring well 100 feet from the horizontal wall, and we put like 10 gauges below the formation to all the way to the top of the, there's a big spread on all of those 10 gauges. And we got the pressure. We had an initial pressure in that area before we started the horizontal development. And after 3 years, we had the monitoring pressures telling us what is the depletion in the matrix at 100 feet from the horizontal wall. So we modeled in the simulation to match all of those pressures after 3 years of depletion. And what we observed was the height that we got is pretty high, and also like the shape in the vertical distribution is not uniform. So you have a big XF in some of the layers. I mean, that's very close to the landing layer, and you have like a truncated version of your it's like vertical efficiency is getting truncated as you move away from the landing zones. So you can also approximate this same SRV volume to a rectangular box assumption. And what we observed was we can still history match it. We can still get the same EUR by doing this, doing the same SRV calculation. But the well spacing is going to be a lot more different when you use a rectangular model versus the ones that closer to the reality. So again, after that paper, we have several monitoring wells that we had in the Permian Basin. We put the monitoring well in different basins like Delaware, Midland Basin, and also we have multiple formations as well. We have Wolfcamp A, Bone Springs, and you can see that the red curve in each of these monitoring wells, that's showing the depletion after few years of horizontal well production, the neighboring horizontal well production. So this is the matrix pressure. So you can see that every time the landing zone has the highest delta P. That means the contribution is coming out to be much more higher from the landing zone. But as you go above and below, you can see that there is a truncation. That means the vertical efficiency is dropping down. So that's where when we model this one, the effect of this, the lower delta P in the top and bottom layers, we found out that the XF is also coming out to be much lower. So that means you have much more efficiency in the landing zone, creating a larger XF and more events. For all these pressure monitoring valve, we have a neighboring microseismic, which we took. And you can see that the blue curves are all the microseismic event counts that we have close by. So it is a very impressive correlation that the event counts are pretty high in the landing zone. And as you go above and below, you can see that the event counts are also dropping in every case, which is also matching the shape of the delta P distribution that we are getting out of all these vertical layers. So we can say, I mean, previously we were thinking that microseismic was too high of a distribution, but in reality, that is what the drainage shape is coming out to be much more realistic. So there is an impressive correlation that we found is we can still use microseismic as a proxy for understanding the vertical height. Of course, there's going to be some cutoff that we have to apply because you are going to be seeing a huge height if you are using every event in the microseismic. So for that, we came up with a workflow. So based on the monitoring wells and the microseismic event counts, we used a cutoff of about 10% of the maximum event counts. If you use that, that is matching pretty much almost like 95% of your SRV drainage. And there are like small event counts in the top and bottom. It comes out to be very insignificant drainage. So you can almost neglect those contributions and get pretty much this. So the resultant height after you put the cutoff, that's what we should be expecting to enter in the RTA height. Because if you don't have this fracture height captured right, I mean, you can still, if you want to match the depletion or the interference, you can adjust your height to a much smaller one and you can have a bigger XF, but you would be having problem when you do that in the multi-stack development because you're going to be seeing interference in the vertical and also the horizontal direction. So anytime you have inconsistency in your fracture height, you're going to be having trouble understanding your multi-stack optimization. So this is, it worked really good because we have so much diagnostics that matches this height. So when we take this, the microseismic and also like the average properties, the way we came up with averaging is you have to have a weighted average because, as I mentioned, like from all the simulation runs that we did, we have a lot more efficiency in the landing zone. So you have to give more weightage to the properties in the landing zone. Otherwise, you're going to be having trouble having some huge swings in the rel pumps by wall to wall, which is not right because some of the zones may be high water, but if the landing zone is still rich, the wall may not be seeing high water oil ratio. So the landing zone is going to be controlling typically a lot of your production and the behavior of the water oil ratio and the GOR. So having more weightage to the landing zone is kind of that's going to be more in line with your consistency. So the way we came out in this example here, I'm showing that the zone 3 is a relatively 100% because that's a landing zone. The zone 2 is going to be a truncated efficiency, and zone 1 is going to be even lower, and zone 4 is 20. So when you use this kind of a weightage with the average pH and the SO pH, you're going to be having an average, because at the end of the day, we still have to have one number input in the RTA. So by doing this back-end calculation, when we treat this as a rectangle box, you're still going to be honoring some of those average, which is physically making sense with the fracture height. Okay, so and also from the microseismic, to have an evidence whether the simulation is coming out to be in line. So we sliced different layers, and what we found out was in the landing zone, you can see that the box size, this is XF, the box size is coming out to be a lot more higher with more event counts And as you go above and below, you can see that the box size have some truncation in the XF with some lower well counts, lower event counts. So this is giving a shape of a teardrop. I mean, that's how we typically see that it's not going to be a uniform rectangular shape. You have a lot more efficiency in the landing zone. That's where you are creating a bigger, like, half lengths. And as you are going above and below, you have like lower vertical efficiency, lower XF. So that's why this shape is kind of much more meaningful, because we have several microseismic pointing out to be that direction. And when we did the simulation matching the pressure monitoring well, we also get a shape which is very, very similar to this. So we are going to be generalizing this shape to understand. So it's not going to be an accurate number that we want to get. We want to see the direction, whether it's matching our expectation of understanding the interference. Now, how do we optimize these multi-stack development? So also, like, for different well types, you have standalone, semi-bounded, and infills. So what we observed was the event counts is pretty similar. I mean, even for the infill wells, you're creating a bigger, like, hydraulic half-length. But when you do the RTA on the infill well, it's going to show a very smaller tank compared to a standalone. That's because you have a lot more shared events, which are not going to be contributing equally like a standalone. So that's the main difference. Your hydraulic half-length is still pretty high for all the infill wells as well, and the semi-bounded. But because of the overlap, your RTA is going to show you a smaller half-length. So you have to have a different conversion for infills, standalone and semi-bounded, to account for the hydraulic half-lengths that you're creating. So, we have several microseismic in the Permian Basin that we collected. And for each of those microseismic wells, we did RTA in that specific well. And what we did was we just found out the relationship between what is the hydraulic half-length from the microseismic for each of these cases, to what is the RTA half-length that we got out of all of those different wells. And again, we categorize into standalone, semi-bounded, and infills. You see, like, the RTA half-length is going to be much lower in the standalone, so you need a bigger conversion to get to the hydraulic half-length. For the standalone wells, a general rule of thumb is, if whatever the RTA half-length you get, if you multiply that by 4 times, it comes out to be very, very close to explaining the standalone performance in reality. For the semi-bounded and the infill wells, is going to be high. Again, for infill wells, we have a wide variety of different spacing. So it's a general, we took an average spacing for the Permian Basin. I mean, it's more like 8 wells per section. But if you have a different spacing, this number is going to be slightly different for each of those spacings. So we are not, again, like, this is not an accurate quantification. This is more like the direction that we have to use all of these diagnostic tools to our advantage. So let me explain, like, what this means. What does this conversion means? So in the RTA model, like, the drainage boundary and the SRV boundary is pretty much, that's what you're going to be draining. Even if you can put some outside boundary, the drainage is going to be very, very less. So your SRV is what is going to be draining pretty hard. So if you can approximate that as a drainage boundary, so you're going to be getting the red box and the blue the blue color. It's all going to be the same. But in actuality, the blue rectangle here is distributed asymmetrically in the vertical direction, right? So your half-length is going to be higher in the landing zone, and you have a truncated events above and below, giving you the same area. So the blue box here and the blue total area here is pretty much the same. But the bigger half-length in the landing zone is what is going to cause interference in the neighboring wells. That's why your actual drainage box is going to be a lot bigger for these, multi-frac wells. You will be having a lot of undrained pockets here and there, but that's the nature of the development. I mean, you cannot have 100% efficiency in these systems because you will be having interference a lot more in the landing zone for the other wells. So that's why this conversion is from this red box of RTA to the red box of this actual distribution, it's about 4 times you have to multiply. So now if you plan your field development plan spacing based on this RTA XF, what happens in reality is you're going to be seeing a significant interference because that's how the nature of this conversion looks like, is you would be interfering a lot more when you don't have any interference based on the RTA. That's why like many of the early developments based on the RTA were like coming up with significantly lower production than expectation. So the validation for this one, so we have a fully developed DSU where we put a lot of pressure gauges, downhole pressure gauges, and we did a lot of staggered flow back to understand the SRV connection early on. So here it's I'm showing you all the red circles here. Those are the wells with downhole gauges, and we did a staggered flow back to understand the impact of the one well interfering with the other well. For instance, for the first example, like I'm going to show you the well 4 and 7, we started first, followed by 5. So when we did that, well, so the top one is the infill 7 pressure gauge response to when we started the production. And when infill 5 comes online after some time, you can see that the pressure starts steepening. So this is the blue dashed line is the expected pressure trend, and you have a big change in your behavior once the 5 came on. Same thing with the 4, it was producing, and when infill 5 came on, you can see that it is deviating from the expected pressure trend, suggesting that there's interference between wells 4, 7, and 5. But in when we did this RTA, even after correcting for water, you are not able to explain the interference here. But now when you correct it to a teardrop shape, so now you can see that 4, 5, and 7, they're all connected SRVs. So of course, like one of the well comes on, you're going to be seeing that some kind of a pressure change from all of those. So this may not be an exact quantification, but it's directionally it's coming out to be explainable why you should be seeing some deviation in the pressure trend when infill 5 came on. So another instance where we did the infill 1 first, and then we got on the staggered 2, 3, and 4 later. So this was the first pressure response of the infill 1. And when infill 2 came on, you can see that there is a deviation from the expected pressure trend. And later on, when infill 4 came on, there is another deviation from the expected pressure trend. And finally, when infill 3 came on, we didn't see that much of expected change in the behavior. So again, like when you look at these SRV shapes, nothing will explain anything based on how the SRV size is. But when you convert it to this kind of representation, you can see that now infill 2 and 1, you should be having some interference. That's why the pressure was changing. And infill 4 and 1, you should be seeing another pressure change because there's some interference. But infill 3, there's a little bit of a diagonal difference in the landing. So when you converted that one, you don't see that much of interference. So again, like that's why you don't see that kind of a pressure change. So again, this is qualitatively helping you to understand how the SRV shapes are distributed. And using this one, we can optimize the future DSUs, how we should be shaping all of these, changing the vertical and horizontal distance to take advantage of this learning. So another validation that we did was the HFTS2, where we had this Bitterroot 1 edge and the boxwood 2 edge. So we have the defit in the boxwood 2 edge. Again, like that was showing some depletion at the toe end. That with the rectangle model, you can add match that defit pressures. So again, when we use microseismic, we can see that like there's like some pressure, there's like fracture trend propagating all the way to that location, and you can see that the resultant XF is about like 3 to 4 times, which is matching the ones that I gave you in the last thing. Is after all these SRVs, you need that 3 to 4 times conversion for the standalone to even explain why any kind of interference or the depletion at that location. And in last year's ATCE, we presented a case study overview based on this. So we selected like 4 different DSUs, developed kind of like in a different like staggered spacing. But what we found out was, okay, so in all of these case studies, we have very similar geology, very similar petrophysical properties. You can see that these are the location. They are like within like a few miles away, but very, very similar properties, very similar reservoir fluid, initial pressures. Your flowback strategy was also pretty much the same in all of these DSUs, similar lateral lengths. In terms of completion, there's a lot more common in case study 1, 2, 3, and 4. We have the first standalone well is the Gen 1. The later on wells, it was a Gen 2 completion. It's a bigger completion. Except the case study 1 was done with all the Gen 1 completion, and it's the same landing. So that's the only difference between the case study 1 and the rest of the case studies. But there's a lot more similarity in the properties and the way we flow back. So everything is pretty much the same. So we should be able to get pretty much a meaningful answer by comparing all of these case studies. Okay, so again, we did the same way we did the RTA conversion, the initial RTA for all of these wells within the case studies. So one of the, the usual observation is these RTA half-lengths are very smaller in general. And you can also see the development timing. The first set of wells are marked with blue. In the case study 1, all the wells came up at the same time. There was no standalone. But in all the other case studies, there's a blue well here, so which is done with Gen 1. Then the second set of wells are the green ones. So those came up at the same time. Third set of well is the red one, which came a little bit later. And then the last one is the black one. There's only one. We have 4 sequence in the case study 4, but the rest it's like 3 different development timing. So again, if you look at this, for example, like case study 4. So we have this RTA when we did for all the wells. We have fracture diagnostics, everything here, calibrated fracture height and the average, everything. So what I'm using here is the total fluid for all of these wells as a guide. So when you're comparing the SRV size, you should be always comparing the total fluid or the total liquid, however you want to, if the gas-oil ratio is not climbing. If you only take a look at the oil, you're going to be having a false correlation because the petrophysical quality is not the same in every landing. For example, if you have the same total fluid in well 2 and 3, well 2, 3, and 4, but when you look at the oil, they may not be the same. Again, like well 4 has much lower oil compared to the well 2 and 3, so that's because the water saturation is different. So that's why you should only look at the total fluid when you compare the SRV changes, because the FRAC doesn't only bring the oil, it also brings the total fluid. So you will be ending up with a false correlation just by comparing the oil alone. So just a caveat. So when you compare the total fluid, you can see that the well 1 almost got smashed when the other 3 wells came on, the green wells came on. So the green wells came out after 15 months. And the well 1 SRV didn't recover after the production of those wells. But in the RTA, we don't see that kind of interference. All these box size are pretty much it shouldn't be interfering, but we do see a lot of interference. So again, we'll follow the normal workflow that I presented. First is so correcting for water. So all of these case studies have water-oil ratio pretty high. So when we correct for the water-oil ratio, now you can see that there's an improvement in the SRV shape. Still, it's not going to show you the interference that you would see in the production. So that's where the correction comes in. So when you correct it to a teardrop shape, now this is how the overlap looks like for all of these case studies. So case study 1 with all the Gen 1 in the same formation, you can see that there's quite a bit of overlap between those wells. Whereas the staggered development, you can see that the overlaps is pretty minimum. I mean, there is still overlap between the walls, but not to the point that the case study one is pointing to. Again, for case study one, we do have microseismic. Again, this entire workflow is coming from microseismic, so it should be, when you back calculate, it should be matching the microseismic. So again, like the amount of overlap is very, very reasonable with what is happening in reality. And all of these walls came up at the same time. There was no standalone wall here. So again, like most of the well performance is hugging on top of each other because there's quite a bit of overlap. So when you start producing, they will all be splitting the SRV. So the only wall, the wall one, which is slightly higher, is because of the edge effect. But nevertheless, I mean, these wall performances are pretty similar. So now going to case study two, now you can see that the wall one was a Gen 1 completion with a smaller height and a smaller coverage. When well 2 and 3 came up with a bigger completion design, it almost like killed the well 1. The well 3 had a bigger overlap with the well 1. So that's why you can see that the well 2 was higher SRV, and well 3, even though you created a higher SRV, you have some kind of shared protection with the well 1. That's why some of the depleted events caused the well 3 to be lower in performance in total fluid. But well 1 got almost like hit really hard, and you can see that the SRV didn't recover that much after that. So because of high overlap between the well 1 and 3, so you have a significant change in the performance in the well 1. So when well 4 came on at the later time, you can see that the well 2 and 3 had some impact in the well 4. The SRV is not that big, so giving you a sense that depletion is really affecting the well 4, even though it is an edge wall. So it came up after 26 months. So it's about 7 months after the well 2 and 3 came on. It got affected by depletion as well. So with this shape, you are able to explain some of these, why the interference is causing. It will also be helping us to better optimize the future SRVs based on the understanding that we have. Again, in case study 3, you can see that this is pretty much of an ideal case where you have a good, healthy overlap. Again, the well 1 was the standalone wall with the Gen 1 completion. So the distance is a little bit more. So there is interference can be explained in different ways. Either it could kill the parent wall or the child wall will get compromised, one of the two. So in this instance, well 3 got compromised. You can see that the well 3 SRV was much lower, but it didn't affect the well 1 that much. So you have slight deviation from the previous performance in well 1, whereas the well 3 is a lot lower. But the well 2 came on like really good because there's not much overlap between the well 1 and 2. But when wells 4 and 5 came on, it did got some amount of SRV compromise because of the well 2 and 3 producing for about like 30 months. So that is quite a bit of a depletion. So your SRV size is lower compared to the well 2. But they're also like, hugging on top of each other. That means there's a lot of SRV overlap between 4 and 5. So this explains that what is the resultant kind of like the configuration that we got. And again, so this is still a good average, healthy average for the DSU. In case study 4, so we have 3 wells coming after 15 months of the standalone production. Now you can see that the well 4 had a big impact on the well 1. You can see that it's almost flatlined after these 3 wells came on. That means the well 1 didn't recover at all from the FRAC kit. So that's because there's quite a bit of overlap between these. And all the 3 wells were pretty much on top of each other. But well 5, it came after like 8 months of the 2, 3, and 4. It got affected by depletion. Now you can see that the SRV size is pretty small in that wall. But well 6 is an edge wall which came many months later, but it's an edge wall with a more staggered distance. So that one came out to be pretty strong as well. So this allows us to optimize some of this spacing is how, after like so many months, how much distance you got to be giving so that you have an LT average that you can expect out of these. So these are some of the direction so this by no means it won't be a quantification of the SRV size by exact means. This is just like an understanding of how these interaction happens in the vertical and the horizontal space. Still, I'm using RTA for understanding all of these. And you have the total fluid, which is guiding you to whether the shapes are looking very reasonable here. So one thing that we understood out of this exercise is when you have a straight landing, you can see that the total fluid for the DSU, and if you normalize to the footprint, so the horizontal footprint, it's much lower compared to the other case studies. So that means staggered development definitely improves your average for the same footprint. So the total fluid is all like in all the other case studies are coming out to be higher, even with the different timing of development, it's still beating the straight ones. So even if you have done the case study 1 with Gen 2 completions, your overlap is already pretty high. So you would be expecting maybe a very minor change upside in the production, but not a whole lot, even if you increase the completion size by a whole lot. So that's why the staggered development is a much better way, because typically your landing zone is what is contributing pretty high to your section contribution. So when you stagger these wells, you're getting advantage of this, the other height, which is not getting equal efficiency to kind of stitch together to have a DSU average, which is like still higher. So again, one caveat in the staggered development is if you have unfavorable petrophysics in some of the landings, that's going to affect the DSU average, because if you have a high water in some of the landings, it's going to be connecting all the SRVs together. So that high water is going to be felt in the entire DSU, and your average may be coming down in oil, but the total fluid may still be looking like pretty high with the staggered development. But yeah, that's where your economics is more on the oil side. So, but your SRV is on the total fluid understanding, but you still have to make money. So that means you have to understand the petrophysical differences in different layers to make this staggered development a success. So recap of what I presented so far is, when we started the RTA on a single phase flowing metal balance volume, you can see that the XFs are pretty small. But when you account for the water protection, you have an improvement in the SRV, but still doesn't explain the interference because of the simplified geometry that we use, which is a rectangular geometry. Again, like fracture height is a very important thing. If you have inconsistency in the fracture height, you cannot optimize the stacked pay development, because you need both vertical and horizontal optimization spacing. So just by horizontal optimization, it's not going to improve the DSU average. So you have to understand what is the right fracture height and how do we take the averaging of the petrophysical properties within that thing to input in the RTA as a single number. And the workflow that we did was we used the microseismic walls as a guide for doing RTA on those walls, and we kind of empirically observed what is the correlation that you need to get that RTXF to reasonably represent your microseismic hydraulic half-length, because that's where the interference comes in the picture. And with that one, we were able to validate with a lot of pressure gauges as well, and also the case studies were giving us a much better understanding of how these wells interact both on the horizontal and vertical space. With this, our conclusions are you have to correct the flowing metal balance volume to account for water protection, at least in the Permian Basin, because your water ratio is pretty high. And you have to, again, convert this rectangular half-length. I'm using microseismic data heavily here because that's more, we have a lot of density of microseismic data, but by no means that is the only data that you should be using. If you have another diagnostic data where you can calibrate these, the half-lengths and the height, you can use any kind of diagnostic data, because all you have is the RTA half-length and something to go with the reality. So again, here, we provided empirical conversion as a guide for to adjust this RTA half-length to reflect the hydraulic half-length. And what we found out from all the pressure monitoring wells are the vertical drainage is not uniform. So that's where the staggered development is going to be coming handy in bridging the gap for some of the layers. If you're high enough from the landing, you are not draining efficiently. That's where the other well in the different landing can take advantage of. And again, we found that drilling monitoring wells was very, very helpful in understanding all of these different fracture dynamics that's happening, and how after many years your pressure change is happening in different layers and matrix. And so we have several simulation models to properly account for all of these physics. Okay, that's pretty much all I have. Thank you very much.
Awesome. Thank you so much, Vivek. Tons of questions. I get questions every time we do these webinars. I get questions on my phones. I get questions on my LinkedIn and on in the chat box here. So one thing I've seen a lot of people love this presentation, by the way. That's the first thing. Can you just condense in a very kind of short manner how you apply this when you go to areas and wells and pads where you don't have all this data? Like if you go to the only thing you have is maybe rates and pressures versus time. Are you simply just applying those multipliers you kind of empirically derive from these other or from these places we have a lot of data, or can you elaborate a little bit on that?
Yeah, so for all of the standalone wells, what we found out was the multiplier if you use about 4 times is pretty much in the ballpark of expected SRV. So we do RTA on all of those standalone wells in different kind of in an area where you are interested in getting a development plan. We do the standalone RTA first, and we apply that 4 times conversion, and we use that as a guide for stacking these wells. So if you use the same shape and create multiple instances in both the vertical and horizontal space, how the overlap is. You need some kind of overlap, but not a bigger amount of overlap to reduce the efficiency of all of these SRVs. So that's where we allow for 10 to 15% overlap, because there may be some uncertainty in our prediction as well. So that 10 to 15% overlap is still needed for better understanding of. So we just place all of these in different vertical and horizontal space to see how the SRVs overlap. So from the standalone point of view. And then when we start the development, we back calculate what is the actual SRV telling us when we started with this assumption, and how the SRVs actually ended up with based on RTA of every single wall later on as a postmortem. And we see pretty much it's not too much off from that kind of viewpoint. Is the well performance are very consistent after we started doing this kind of development plan. It's more in line with our average expectation for that one. Our typal profiles are much more reasonable. We are not seeing, I mean, of course, you are going to be having that in one-off wall, having a bigger swing. One wall is going to be higher, one wall is going to be lower. That will happen in actual development. On an average, the expectation is coming out to be in line with the well spacing that we have. So that is a big advantage of this one, because previously we have to have a cookie cutter spacing, but that's not what we should be doing, because every standalone wall is giving you some idea about the DSU. So whether you're going to be having a bigger SRV to begin with or a smaller SRV, that could be a multitude of properties that you have. You have a lithology difference, you have a permeability difference, your porosity difference. So your SRV size is going to be different for each of those, and your geomechanical properties is going to be different. Your height is going to be somewhere it's going to be higher, somewhere it's going to be lower. So once you have a diagnostic for the height, that's all you need. So then you can use this to get a meaningful representation of your DSU overlap, and then you do the actual development based on this one, and you just compare your actual production with this expected production.
Awesome. Very quick, do you think do you think no overlap is the best, or some overlap, some interference is actually good, or in an ideal world would you like it to be interference?
Yeah, definitely some overlap is always better. no overlap is going to be really, really, it may not be an ideal. Like, what if one wall doesn't perform as expected? That means you're leaving a big gap there. So I would expect at least there should be at least like 15% overlap, so that you have, even if you are sharing the conductivity, is really good for the early time protection as well. So I would expect like some kind of overlap is definitely needed.
Awesome. We have a question from Austin, and that will be the last question. I see some people ask about when we're going to get this into Whitson Plus. Applying simple multipliers of 4, I think we can do that already. But what we need there is like we have a multi-layer model, but being able to essentially have different accepts for different layers, and that's what I'm pushing my guys to get into our next release, at least very soon. So that's the missing piece if you actually want to model it.
Yeah, here I'm representing a very, very simple geometry, but I would recommend that if you have a very much all the data needed for some kind of fracture modeling, and use that shape to kind of replicate all of these SRVs, I think that is a better way to go, because you have all the modeling, physics taken into account in the modeling. So once you have the SRV size, I think like that's what is going to be really helpful.
Yeah, 100%. Last question from Austin. How do you reconcile hydraulic versus conductive fracture dimensions? Is the assumption that the SRV via microseismic is a proxy for drainage dimensions?
Well, there will be some uncertainty with the microseismic half-length. I mean, it's not going to be perfect, because you are measuring the shear events versus the compressive, fractures. There may be some uncertainty in your hydraulic half-length, but at least it's a good starting point compared to what we have already. I mean, it's what we have as a rectangle model is not even close. You're like way too far off. So anything which bridges the gap is still a better starting point. I mean, you may not be having 100% right. That's where, like, if you have another diagnostic tool that you can combine with, I would always try to do multiple diagnostic tools, because that's where you get more strength. You can even look at the FRAC kits in the neighboring worlds to understand how far these hydraulic half-lengths are getting extended. So there are multiple ways to do the same, to get to the same shape. Yeah.
Okay, awesome. With that, Vivek, I see there's tons of questions here. We'll not be able to answer that, but I'm sure you'll be at different conferences and stuff this year, or you can send probably Vivek an email to discuss more. Really appreciated, sir. As I mentioned, one of my favorite papers, or a couple of papers from last year. Awesome stuff, and I think it's a little bit of an eye opener for there's a lot of people in the RTA community, because that's kind of where they've been resolving an A-K and maybe a contacted pore volume or an SRV or whatever we would like to call it, but translating it into geometries that actually make sense and match what you see in the field has been where people have really burned themselves just because of this rectangular assumption. So really appreciate it, and you have a good rest of the day, and thanks everyone for joining.
Thank you very much.